Welcome to Garrott CompSci. Today we're going to explore the concept of number systems. Number systems are just any way that we could use symbols to represent values, numeric values, numbers of things, amounts of things. Everyone knows that one of the most famous concepts in computer science is learning binary numbers, because binary is the number system on which computers operate and store information. So one number system is binary, and one number system is called decimal. Computers use the binary system for absolutely everything. Decimal is our everyday number system that we use for money and counting things and everyday conversation about quantities and values that are numeric. So let's think about the decimal system a little bit before we try to dive into binary and other systems. As I said, decimal is our normal everyday number system. It's based on the values 0 through 9, the shapes, the symbols 0 through 9. This is also known as Arabic numerals. Arabic numerals seem to be the main thing that we've used, and you might assume that we've used them forever. But they were actually developed by Hindu mathematicians, that is, mathematicians in India around AD 500. So it was not all that long ago in the history of humanity that we invented these numbers. And then they were adopted and refined by Arab mathematicians, for whom they're named, in about the 8th or 9th centuries. And they didn't spread to Europe until somewhere between the 10th and 13th centuries. So at the very earliest, they were reaching Europe by the 900s. So not all that crazy old compared to what you might assume. So like I said, let's look at the decimal number system, which we also call the base 10 number system. And notice the base 10, or DEC, number system has the digits or shapes or symbols that represent values. The digits we have in the decimal or base 10 number system are 0 through 9, so not quite 10. Now we'll come back to that. In the base 10 number system, when you were learning it in elementary school, it's very likely that you started with place values. So I'm going to come up with a base 10 number, 2,375. And in elementary school, it's likely that you numbered your place values. So you probably remember this is the ones place, and the tens place, and the 100s place, and the thousands place, and it would go on forever. You may have also had to do what's called a place value expansion. So that's to break down the value of this number based on each individual digit. So what we would do is multiply the digit in each place by the place value that it's in. So this first one would be 2 times 1,000. And then we would add that to the same operation in each place value. So this is 3 times 100. And then 7 times 10. and then 5 times 1. And then, of course, we could go 2,000 plus 300 plus 70 plus 5. And, of course, again, that adds up to 2375, 2,375. And so this expansion helps us understand the value of each digit in the place that it's in. Let's explain one step further why these place values are what they are. As I said, the decimal number system, our everyday number system, is called the base 10 system. And if you think back to algebra, we have bases are paired with what? Exponents. So for example, you can have a base 2 to the power of 3, or the exponent 3 is equal to 8. This big number is called the base. So if we have a base 10 number system, each place value is base 10 to some power. Now think back, 10 to what power is equal to 1? It's 0. Anything to the power of 0 is equal to 1. So this is the ones place because it's base 10 to the power of 0. And we always start with the 0 power on the right. Then, you might have guessed by now, this is 10 to the 1. 10 to the first power is equal to 10. So that's the tens place. Base 10 to the power of 2, or 10 squared, is 100. And 10 cubed, or 10 to the third power, is 1,000. And so on, forever. So instead of saying 2 times 1,000, you could also say 10 cubed here. 2 times 10 cubed, and 10 squared, and 10 to the first, all the way down to 10 to the 0. Always remembering that the 0 power is always on the right. Okay, so now that we've explored this for base 10, so we often think binary seems like something alien, something entirely different than the numbers we're used to. But the binary system works exactly the same way as the decimal system. The only thing we change is the base. So as decimal starts with this prefix dec, meaning 10, so that decimal is the base 10 system. Binary starts with the prefix bi, which suggests it's base 2. And if the decimal system, base 10, gives us the digits 0 through 9 to play with, you might guess that the base 2 system gives us digits 0 through 1, not quite 2, to play with. So let's go to a new page. So this is the binary system, aka base 2, with digits 0 through 1, or just 0 and 1. And so just like before in the base 10 system, we have our place values, and of course they go on forever to the left. On the rightmost place, we have the base, which in this case is 2, not 10. Base 2, and again we start with the power of 0, and then we go up from there. And so on. 2 to the 0 power, like anything to the 0 power, is the ones place. And 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. and so on. So you might have noticed, whereas the base 10 system has us multiplying by 10 each time we go left, the base 2 system has us multiplying by 2 each time we go left. So we always start with the ones place in all number systems. And then in base 2, or binary, we double each time. So the ones place, 2, 4, 8, 16, 32, 64, 128, 256, 512, and so on. You may have, that may have triggered some memories or some connections to other computer concepts like the size of a hard drive or the size of a storage device like a flash drive, or the storage amount of iPhone models, things like that. So you start to see the powers of 2 all over computer science once you know what's going on. Okay, so we all know that binaries are numbers made up of zeros and ones only. So I'm going to fill in just a random binary number. I made this up. We would not say this is 10,110 because that's using base 10 or decimal terminology for the place values. So we would just say 10110. And now we're going to expand this value just like we did for base 10 earlier, based on the place values, which are different now, but the process is the same. We're going to take the digit that's in this place and multiply it by the value of that place. So 2 to the 4th, or 16. So 1 times the 16's place, added to 0 times the 8's place, added to 1 times the 4's place, added to 1 times the 2's place, and added to 0 times the 1's place. And if we go through that, anything times 1 is itself. Anything times 0 is 0. So that's 16 plus 4 is 20, plus 2 is 22. So this value over here, 10110, in binary, and I'll write it like this for now, is equal to 22 in the decimal system. Now, when we're comparing two numbers that are the same value, these are the same value, just in different, expressed in different number systems, we like to put a little subscript, meaning right below, written below, to say what number system they're expressed in. So we could write this little abbreviation, but more common is to write it like this, 10110 base 2. So you put a little 2 below the number, kind of the opposite of an exponent. And that's equal to 22 in base 10. So this is how we would write our final answer, expression of the answer that we found just now. Now, let's notice a pattern here that makes converting between a binary number into the decimal system very fast, very simple. Again, I said we expand these out by multiplying the digit that's in each place by the place value of that place and adding them all together. But since we only have digits 0 and 1 in binary, every time we're multiplying by either 1 or 0. So we either add up that place value or we don't when it's a 0. So we add up that place value 4 and that place value 2, but we can skip it if it's got a 0 in that place. So the fast way, when you see a number like 10110 in binary, to convert that to decimal, you can write out the place values under each digit, starting at the right, always with the ones place and doubling. And then you can go through and add up the place values that have a 1 in that spot, skipping the place values that have a 0. So again, we have 16 plus 4 plus 2, which is 22. Notice this is all the same as what we did up here. So that's going from binary to decimal. Let's just do a couple little examples of that. This is binary to decimal. Just one more example or two. 11011 in base 2 is what in base 10? If you're doing this for class and you have this on a quiz that's on the computer, I suggest you actually use a pencil and paper always to write this out, because even if there are some that are a little bit easy to see in your head, it is so easy to get off just by one place value. So as long as I've been doing this, I still write this on paper so that I can label my place values. So remember, this is the ones place. Start with the ones place at all times. This is the 2s, the 4s, the 8s, the 16s. Not too hard to start with 1 and double each time. And as you do that, it'll become very repetitious, very easy to remember in your head, even up to the high values. And then again, you add up all the place values that have a 1 in that spot. So in this case, 0 is only in this one. So we're going to add up this and this and this and this. And of course, you can find the easy things to add that come up with 10. So there's 10 and there's 17. So this is 27. Okay. There's one more example. If you'd like more examples, it's very easy to find. You can Google binary to decimal conversion practice. You could ask your favorite AI chatbot to come up with some examples, and it'll probably even give you an answer key to check your work afterward. Just remember to use that honestly and not to skip your learning process, but to reinforce it. So find some examples either in class or from your teacher or from the internet, and do a few more. And find a good way that you like to show your work on paper with a pencil and stick to it. Having one good way of showing your work helps reinforce your confidence in any task like this. Okay, so now let's go the other direction. So not binary to decimal, but decimal to binary. This is decimal to binary conversion. So if I had a value like 43 in base 10, and I want to convert it to binary, there are several ways you could find on the internet that suggest how you should do this. Many of them are good, but I find that many of them are a little bit clunky to show your work on. And as I said, I believe strongly in having one very solid way that you can depend on of showing your work to go along with your understanding of what's going on mathematically. And so this is the way I've always taught it. I start by writing out my place values, and I usually even draw some blanks to keep things nice and clean. And I'll keep adding blanks as far as I need. I don't always immediately know how many blanks I'll need until I start writing them out. So what's on the right? Always the ones place. And then double to 2 and 4 and 8. And notice I'm going to be converting 43. So I'm going to keep going until the place that I would add goes above 43. So 16, and the next one is 32, and this next one would be 64, and that's bigger than I need to make 43. So I'm going to stop right there. No big deal if you went one or two too far. They would just start with zeros, and at the end you could cut them off. So I've got my place values written out. I'm going to convert 43 into these place values. The first thing I do is write above the blank, small, the number I want to convert on the left. And then I ask the question, do I need 32 to make 43? Do I need to use this place 32 to make 43? Another way of saying the same thing I mean here is 32 less than or equal to 43? And yes, it is. So I'm going to put a 1 there to say I used the 32 place. Once I use the 32 place by putting a 1 there, how much is left over from 43? Well, that's 11. 43 minus 32 is 11. So I'm going to go to the next place and say there's 11 left to convert. And again, I ask the same question on each place. Do I need 16 to make 11? In other words, is 16 less than or equal to 11? And it is not. So I'm going to put 0. And I didn't use this place, so I didn't subtract anything from what's left to convert. So I'm going to continue with 11 here. And ask the same question. Does 8 go into 11? Do I need 8 to make 11? Yes. 11 minus 8, once 8 is used, I have 3 left over. Do I need 4 to make 3? Is 4 less than or equal to 3? No. So there's still 3 left to convert. Do I need 2 to make 3? Is 2 less than or equal to 3? Yes. 3 minus 2 is 1. So there's 1 still left to find. And of course, just adding 1 will get that. But I can ask that same question. Is 1 less than or equal to 1? Yes. And what's left over? 0, as it should be. Nothing left to convert. So that's the process I use to go from decimal to binary. So the answer here is 43 is equal to 101011 base 2. And if I wanted to go ahead and check my work the other direction, I could just quickly look at where all the 1s are and add up the place values underneath all the 1s. So here's 8 plus 2 is 10, and 32 plus 1 is 33. 33 plus 10 is 43. So that's right. So once again, I could find more. You can find more examples of conversions between decimal into binary on the internet all over the place. And you can practice going in both directions by first doing this and then going back the other direction to check your work. So now we've accomplished decimal and binary conversions back and forth between the two systems. Those are usually the most important conversions to be able to do for various computer science classes. And as I said, binary is going to be the most important because computers operate entirely on binary. Everything you see in the computer is represented using only ones and zeros according to various schemes for how they show all that those different types of things like text and colors and videos and pictures and all of the different things that go through your computer. Okay, so let's go on to another thing to notice, which would be counting in binary. Not a whole lot to do here, but just a few things to notice. So what is 0 in base 10 is also 0 in binary, right? They're the same thing. So let's start with 0 in binary and start counting up. So in base 10, this is decimal, and over here will be binary. So in base 10, we can count 0, 1, 2, 3, 4, 5, 6, 7, and so on. We'll keep adding to that in a moment. But in binary, I only have the shapes, the digits 0 and 1. Now, notice in decimal, I've got all these shapes 0, 1, 2, 3, 4, 5, 6, 7, and then it continues with 8. I'll continue this like this. And then 9, and then remember decimal has shapes 0 through 9. And so when I run out of shapes, what do? I set this last place value back to 0 and I add 1 to the next column. And then I can continue from there. And once I get up to 19, I've run out of shapes in this place value. And I can start over again at 0 and add 1 to the next column to make 20. And then I won't go another 2 columns, but if I go all the way up to 98, 99, now I've run out of shapes, run out of digits for 2 of these places. So both of them set back over to 0, and I add a 1 to the next column to make 100. So hopefully you see the pattern there. Now, what do we do in binary to do the same kind of counting? The same rules apply. We just have far fewer digits. Just have 0 and 1. So 1 in binary is just going to be 1, because this is the ones place to make 1. And then we've run out of shapes already. In one place value we had 0, and then we had 1, and those are the only 2 options. So I'm going to start it back over at 0 and add a 1 to the next column, just like we did over here. So 2 in decimal is equal to, not 10, we don't say 10, but 1, 0 in binary. And thinking back to your place values, you should be able to confirm that, because this is the ones place and the twos place. Okay, and now we've got a place here. We can add 1 more in this place value, 1, 1, and that's 3. Because this is the ones place and the twos, so 1 plus 2 is 3. Now, just like over here, we had the maximum digit and the maximum digit, and so the next one sets both of them back over at 0 and adds 1 to the next column. So maximum digit in binary is 1 and 1. So both of these set back over to 0, and we add 1 to the next column. So 1, 2, 4. There's 1 in the 4's place, so that's 4. And so just watch as I fill this out and notice the pattern. So we always fill up from the rightmost place, and then we use that little starting back over at 0 pattern that we just saw. So the next one will be 101. And now this one is full, so we move to 110. And then finally 111. 1 plus 2 plus 4 is 7. And now all 3 of these spots are at their maximum digit, so we set them all back over to 0 and add a 1 to the next column to make 8 in decimal. 1, 2, 4, 8. And now I'll just continue. These are both full. They're both maximum, so we set them back over at 0, add 1 to the next column. That's 1, 2, 4 plus 8 is 12. So hopefully you see the pattern there, and you could count in binary. One little interesting thing to notice here, look at 7. They're all 1s, right? So if you had a long string of 1s, 1, 1, 1, 1, 1, there's 5 1s. The value here is going to be 1 less than if the number were all 0s here and another 1. So this is the 1s place, the 2s, the 4s, the 8s, the 16s. Okay, so it would be adding all of these up, right? But a little shortcut is the next one would be the 32 place. So the next number would be setting all these to 0 and adding a 1 to this place, making it 32. So what it means is all of this is 31. Just a little thing to notice that might save you some time. So by learning our counting in binary, and by learning the foundations of the number system, by expanding all the place values and seeing how it relates to our regular decimal numbers, and by noticing these little patterns of counting like this, we've drawn some connections that'll help you understand what you're doing when you convert between binary and decimal. Understand a little deeper how the computer is using binary in ways that are already very similar to the numbers that we use every day. And hopefully it makes any work that you're required to do for class or for any projects you're working on a little simpler and maybe feel a little less alien to you. Now, I'm going to go back to the beginning for just a moment to number systems. Remember we had this for base 10, and then we did the same thing for binary where we just had a different base. So all the place values were 1, 2, 4, 8 instead of 1, 10, 100, 1,000. Just want to let you know that there are more number systems than just binary and decimal. There are all kinds of weird ones. We have binary, which is base 2 with digits 0 through 1, which is just 0 and 1. We have decimal, our everyday numbers, or Arabic numerals, 0 through 9. That's base 10. Another one often used in computer science is octal, and you might guess oct means 8, base 8. Think what digits do you think are available in octal based on this pattern compared to these? It's 0 through 1 less than the base, so 7. And you could have hexadecimal. That's another one often used in computer science. Usually it's used as a way to express lots of binary in a shorter amount of space. So it's not really used in storing anything in the computer. It's used in talking about lots of binary in a shorter way. And this one's a little weird, but it's hex, which is 6, and dec, which is 10. So this is base 16. Now base 16, according to this pattern, for one place should be able to have digits 0 through 15. But how could a single digit, one place value of a number, have the value 10 or 11 or 12 or 13 or 14 or 15? Well, after we pass 7, 8, 9, then we'd start using letters. So we can use A to mean 10, but in one digit. And B is 11, but in one digit. C, 12. D, 13. E, 14. F, 15. So in hexadecimal, we have the digits 0 through F, meaning 0 through 15. So those are the most common binary number systems. And just to show you, all of these work exactly the same. We could also have some that don't necessarily have commonly used names for the base. It could be anything. It could be, it could be base 11. That's kind of weird. There's no real common use for that. But there could be this, and it would be, 0 through 10, which is maybe A. Or there could be base 7, which is 0 through 6 digits. And all of these are going to work the same way. So let's choose octal real quick. The octal number system is base 8, and it has digits 0 through 7. And just to remember, all of these number systems work the same way. So again, we can't go over 7 in the digits. So what if we had a number like 3, 7, 0, 2 in base 8? What is that in decimal? So again, this would work the same way, but the base is going to be 8, not 2, not 10. So the big number, 8. The exponent, again, 0. 8 to the 1, 8 to the 2, 8 to the 3, and so on if we had more place values. So this is 8 to the 0. Everything to the 0 is the 1's place, the 8's place, the 64 place, and the 512 place. So it gets big pretty fast. So if we wanted to expand this out, we would say the digit times the place value. So we would have 3 times 512 plus 7 times 64 plus 0 times 8 plus 2 times 1. 512 times 3 is 1,536. 7 times 64 is 448. 0 times 8, of course, is 0. And 2 times 1, of course, is 2. So if we add these up, 448 and 1536 and 2, we get 1,986 in base 10. Okay, and as I said, all of our number systems work the same way according to the same pattern. Use the base, start with the exponent 0 and go up to the left, and do your expansion, multiplying each digit by the place value that it's in, and adding up the products. It just happens to be very natural to us in base 10 because we've done that since childhood, young childhood. And base 2 happens to be quite easy because it has that shortcut of only having 0 or 1. So either skip or add each place value based on 0 or 1. But all of the weird number systems you could possibly come up with use that same pattern. And now for the last thing I want to show you. There are some tricks for how to convert between binary and octal, and also between binary and hexadecimal. As I said, octal and hexadecimal are both systems that are used to talk about values in computer science. And so sometimes we like to go between base 2 and octal, and between base 2 and hexadecimal. We've already done between binary and decimal back and forth, which is common. But in computer science, this is also a quite common direction. So let's start with octal. There's a little connection that you might realize by now. 8 is 2 cubed. 2 to the power of 3 is 8. So that gives us a little hint of something we can do as a shortcut. Binary to octal. So if I have 1, 0, 1, 0, 0, 1, 0, 1, 1 in binary, what is it in octal? As I said, 2 to that power of 3 is 8. So I'm going to start on the right side, and I'm going to add a comma, just a little mark, between every triplet of binary places. By the way, one single place of binary, one place or digit of binary has a special name. It's called 1 bit, which you may have heard of. And bit is a contraction, B plus IT, binary digit. B, it, binary digit. So between every 3 binary digits or bits, I'll put a comma, starting at the right, like we do in decimal. And so every single triplet of bits, 1, 2, 3, will go into one single digit of octal. So each of these triplets will go to a digit of octal. So our answer here will be in 3 digits. And the way you do it is you treat each one of these like a separate binary number, and you put your little place values like we've done. This is the ones place, the twos place, and the fours place. This is 1 and 1 in places 1 and 2, so that's 2 plus 1 is 3. And this is just a 1 in the ones place, nothing in the 2 or the 4. Notice we start over for each triplet. So this is just a 1. And this is 1, 2, 4 again. So it's 4 plus 1. Just the place values in where there is a 1 in that spot. So 4 plus 1 is 5. So this big long string of binary is expressed as 5, 1, 3 in octal. Now notice real quick, you can go the exact opposite direction. I'll just use the same example, but you could come up with one yourself as long as the digits stay between 0 and 7, of course. So each digit of octal can be expanded into 3 digits of binary, 3 bits each. So this will be 1, 2, 3 for the 5, 1, 2, 3 for the 1, 1, 2, 3 for the 3. And each triplet will start over with the place values. So this is 1, 2, 4. I can put commas just to help me keep this straight. And then the 1 is going to be in places 1, 2, and 4 as well. And the 3 will also be expressed in these places 1, 2, and 4. So starting at the left or the right, it doesn't matter, but we're going by triplets or by digits of the octal. The 5, what of these 3 bits, 1, 2, and 4, will make 5? We can use our method of putting it up here. We say, do I need 4 to make 5? Yes, I do, with 1 left over. Do I need 2 to make 1? No. So there's still 1 left over. Do I need 1 to make 1? Yes. So that's all of it. Or you could use your intuition and see, oh, that's 4 plus 1 makes 5. So it's 1, 0, 1. Now what of these bits makes 1? Well, just a 1 in the ones place, and the others are 0. What makes 3 for the last digit? No 4. Yes for 2 and 1. 2 plus 1 is 3. So octal 2 binary is the same way. Just give it 3 bits, 3 binary digits per digit of octal. If you happen to have a 0 on the beginning, you could, of course, leave that off. Okay, and again, as always, you can find maybe a little bit more obscure, but easily found with a good Google search or an AI request for some examples of converting binary to octal. Now let's do one more thing. Let's do the same thing back and forth between binary, back and forth with hexadecimal. Now, as I said, and this is base 16, right? And this is 2. The last one was base 2 to base 8 and vice versa. And because 2 to the power of 3 is 8, we could do every triplet of bits. And this one is 2 to the power of 4 makes 16. If you don't understand that math, no big deal. But going between binary and hexadecimal, 1 digit of hexadecimal is equal to 4 digits of binary. So if I had a rather long hexadecimal, let's start with this. Okay, so there's my binary. It's pretty long. If you had this in the computer and you were trying to solve some problems or check your work on a computer science project, it might be a little much to tell someone or to write it down. So we often use hexadecimal, as I said, to abbreviate long strings of binary. And so if I was doing this, not every triplet, but every quadruplet, and I start again from the right. You can't start from the left because it might not be a perfect multiple of 4. But start with the right. 1, 2, 3, 4. I'll put a comma. 1, 2, 3, 4, comma, comma. So for each of these quadruplets, I'll get 1 digit of hexadecimal. So once again, the same as before with the octal. I can start my numbering 1, 2, 4, 8. 1, 2, 4, 8. Start over with each quadruplet. 1, 2, 4, 8. 1, 2, 4, 8. And by the way, if there was a single 1 here, or maybe there were 2 ones, I could start again. 1, 2, and it could just stop there. But let's leave that off for now. Okay, so this one is 8 plus 1, because there's a 1 in there and a 1 in there. So that's a 9 in this first spot. And this is 2 plus 1 in this quadruplet. So that's 3. And this one is 8 plus 2, which is 10. But remember, we only have, we don't want to use 2 different shapes because this is hexadecimal and we want it to be 1 digit. And so that's why we start over with 10 equal to A. And then this is 8 plus 4, which is 12. And if you go A is 10, B is 11, C is 12. So all of this long thing right here is equal to 93AC in base 16, or hexadecimal. And just as we saw before, we can go the other direction easily. We can say 1, 2, 4, 8. And we can say that's 9. Oops. 9. 1, 2, 4, 8. 8 plus 1 is 9. And then we can say 8, 4, 2, 1. 8, 4, 2, 1. And we make 3 there. 2 plus 1 is 3. And then we've got A. So we have 8, 4, 2, 1 again. 8, 4, 2, 1. 8 plus 2 is 10. So 1, 0, 1, 0. And finally C, which is 12. And it's okay if you need to write that over here like this to remember, what it's equal to so that you don't get that wrong. So C is 12. So I have 8, 4, 2, 1. 8 and 4 is 12. So there we are going from that to that. So there's our conversion between binary and hexadecimal. So between binary and octal, we have triplets. Between binary and hexadecimal, we have quadruplets. And if we wanted to go between any base and decimal, our everyday numbers, we want to use our expansion method that I showed you earlier on. So like this for base 10. Or like this for octal. You just change the base and evaluate what each place value is equal to and expand it out and do the math. So as I said, hopefully you have a good, solid understanding of how number systems work, and you are able to make the connections between all of this work that we've done. Not just know the processes for how to do it, but understand why these processes all link together. Again, other number systems are not all that alien from the numbers we're used to using every day. So rewind this video, go back to the part that you didn't quite understand. I feel like my explanation is in a very good order, so if at any point of this you lost track, go back to the first place where you lost track and watch again from there. And rewind until you get it, and then move on to the next page, next section. And as I said, find some good examples on the internet or from a teacher or from class to practice each one. And let me know in the comments if you ever have any questions. Thank you very much. If you don't mind hitting like, sharing this with a friend who could also use this or might also be interested, or, and especially, hit that subscribe button so you can hear what else I have to offer. Thank you. Bye.